Okay, so starting with mass A. Mass A is going to come down and hit mass B. This portion of the string is known as L.
Here's a clean and professionally formatted presentation of the calculation
where L
shown
length
in
of
the
the string and theta is the angle
application
adjacent
of the
to
work
the
energy theorem, WET.
This is the
From the work
portion
energy theorem, the force
mass
F is given
A will
by F
fall.
equals frac
We're going to
text
call this
KE, where
H,
KE
the height
equals
that
kinetic
it goes
energy,
through.
S equals stopping
And so using
distance.
conservation of
given
energy,
for object A,
we're going to
FA
say
equals frac 100,000, 0.10. For
potential
object
energy
B,
at the
FB
beginning
equals frac
is equal to the
225,
kinetic energy it
1500
will
equals
have right before hitting
0.15
mass
text
B.
makes in. And force ratio frac FA, FB equal frac 0.10, 0.15 equal
So the
fractional
velocity
result.
of A
A box
right
frac
before
FA,
it
FB.
hits mass B.
Would you like a PDF version of this explanation?
Using H, which using our numbers given gives us 17.8 centimeters or 0.18 meters as our height. Using 9.8 for gravity. We can say our velocity right before it hits mass B is 1.86 or 1.9 meters per second. Okay. So using that and this is an elastic collision. This is a perfectly elastic collision. So using the equation found on page 262, we can say that our final velocity of mass B is going to be the velocity of mass A times 2 times the mass of A divided by mass A plus mass B and then this VB is the initial velocity of mass B, which it wasn't moving to begin with, so that velocity is 0, which makes this whole portion 0. So plugging in our known values, we have 1.9 for our velocity A. We have 45 grams or 0.045 grams for mass A, 0.045 kilograms, and 0.065 kilograms for mass B. This gives a final velocity for B of 152.9 centimeters or 1.5 meters per second. So this is the final velocity of B after the collision. So if we know the velocity of B after the collision, we know the velocity of A before the collision, then we can use that to solve for the velocity of A after the collision using the conservation of momentum equation. So again, the velocity of B was 0, so it's 0 here. This is the velocity of A after the collision. This is the velocity of B after the collision. Again, this is what we're solving for. So we can say 0.045 was the mass of A, 1.9 velocity of A, 0.065 is the mass of B, 1.5 is the velocity of B after the collision, and this is the velocity of A after the collision. We get negative 0.34 meters per second. This tells us that it's going left. So if we know the velocities of B and A after the collision, then we can go back to the conservation of energy equation. And we say the kinetic energy after the collision is going to be all potential energy when it reaches its max height. So the masses here cancel. So then we can apply the same equation to find the height of A, which using the final velocity get negative 0.34 squared divided by 2 times 9.8. This is the height of A after the collision. And then using the velocity of B, which was 1.5 squared divided by 2 times 9.8, would give us the height of B after the collision. So the height of A ends up giving us 0.5 8 centimeters or 0.0059 meters. And then for the height of B at the collision, we get 0.119 meters. And these are the heights of the masses after the collision.